Quantum computing. Hundreds of companies around the world are all in a race to build the world's first useful quantum computer, using multiple different approaches. They're doing this because quantum computers will, theoretically, be able to calculate answers to certain problems that would be impossible to solve using even the most powerful supercomputers we could ever build.
Quantum computers are, really good at quantum mechanics, right?
Simulating reactions involving quite large molecules, things that we can't do with a classic computer.
Really in the space of material science, chemistry, computational chemistry, these are the problems that quantum computers can really help us solve in a new and different way than we can classically.
I'm in Copenhagen to see a brand new development in the world of quantum computing. I'm here to see some new devices being developed by Microsoft, their bid as they enter the race with the likes of Google, IBM and many others to make useful quantum computers. What's exciting is Microsoft has gone for a kind of unconventional approach known as topological quantum computing, which is incredibly difficult to build, but if they manage, has potentially big advantages over the other approaches. Well, recently they've made some big breakthroughs, and I'm one of the first people who gets to see them and then talk to some of the lead scientists who have been working on this project. I used to work on quantum computers before I became a YouTube science explainer man, so I'm really interested in all these latest developments. The work Microsoft are doing, strangely, has a lot of overlap with the work I did in my PhD 15 years ago. Then I was trying to make a quantum device out of superconducting nanowires, basically tiny little electrical wires, with the lofty goal of building a quantum computer. Unfortunately, I didn't manage to make anything useful. But now I find out Microsoft are making their quantum computers out of superconducting nanowires. So, of course, I wanted to find out absolutely everything. So basically the key thing Microsoft are aiming for is to take advantage of an exotic behavior in quantum physics called topological superconductivity. This is because if you build a quantum computer out of a topological superconductor, it will potentially be a lot more resilient to noise than other designs of quantum computers. Topology comes from the realm of mathematics, and it studies what properties of a thing stay the same when you change the shape of that thing. That's quite abstract, so I've got some examples to help. So take a couple of objects. One simple topological feature of an object is how many holes does it have in it. So even though a mug and a donut are very different shapes, topologically they're the same because they both have a single hole in them. And we can morph from one to another smoothly as long as I don't break it or make a new hole. So even though from a geometric point of view, these shapes are very different, from a topological point of view, they're the same. Another example is to compare a loop of paper to a Mobius strip, which is essentially the same thing, but it's got a halved turn along it, which connects one side to the other side. Now, the topological property we're interested in here is not the number of holes these have, but the number of sides. The loop of paper has two sides, the outside and the inside. But the Mobius strip only has one side because the halved twist connects one side to the other. So even though these two loops of paper look similar, they're topologically different because they have a different number of sides, and you can't morph from one to the other without ripping the paper. So I have my Mobius strip, and it's got physical properties, and it's got topological properties. And if I introduce some noise, basically just by jiggling it about, that's changing its physical properties, like it's where it is, or the specific shape it's in. But it's not changing the topological properties, how many sides it's got. It's still only got one side regardless of how I'm jiggling it. But if I jiggle it about too much, with too much energy, I'll end up ripping it. And now that's changed its physical properties and its topological properties because it's gone from having one side to now having two sides. So most quantum computers are built from the physical properties of a system, electrons or atoms, and so they're sensitive to this physical noise. Whereas what Microsoft are trying to do is build their qubits from the topological properties, which gives them an extra layer of protection from the noise. But obviously, if the noise gets big enough, they're still vulnerable to that too. But the difference between the two is known as the energy gap.
We believe the topological qubit promises to be 100 to 1,000 times better in terms of that base physical noise rate.
Now, why is that important? Well, When us physicists talk about noise, we don't just mean noisy sounds. We mean random bits of any kind of energy. Examples could be radio waves from our phones or Wi-Fi, which are around us all the time, or even background radiation coming from the Earth or from space, or simply the random wobbling of atoms, because they've all got heat energy. Noise is a big problem for quantum computers because they're incredibly sensitive and fragile. For them to work, you need to isolate them from the rest of the world and keep them in a pristine environment away from any noise energy. Because any little bit of noise that gets into the system can completely ruin the calculations.
Right, so we really need to keep it protected, keep it isolated, and keep it clean from what's happening in the world around it, right? Keep it in its quantum computing state.
This is why quantum computers normally look something like this. So basically, inside here, it's at a very cold temperature, millikelvin. This is a massive vacuum can where all the air has been pumped out, and it contains a kind of Russian doll of other vacuum cans. Removing the air means that there's a minimum amount of atoms bouncing around inside, and this also gives it thermal insulation. Each can also has shielding to protect from external radiation. These are all the shields as well to protect it from electromagnetic radiation, phone signals. And it's all cooled to a very low temperature, because temperature itself is a source of noise. Right in the middle of the fridge are the quantum devices that do the quantum calculations, basically the central processing unit of the quantum computer. This core chip can have very different designs in the different approaches to quantum computing people are pursuing, but all the different kinds of quantum computers will be designed to protect the central quantum devices from noise. But the quantum computer Microsoft is building has got an extra layer of noise protection baked into the design of the chip. And what was really cool is I got to see with my own eyes what they're working on. I got to have a tour of the lab where they make their quantum devices, and it was super fun for me because I was just very excited to see a high-quality science lab that was making the kinds of things that I was only able to dream about when I was doing my PhD. Basically, Microsoft has got two labs, one where they make the quantum devices, which involves a clean room, which is a room free of any dust, because even a single mote of dust can completely ruin your devices.
We start with materials growth, where we really grow our semiconductor and get our structure in it. Mm-hmm. Then we have nanofabrication steps, where we definitely borrow fabrication processes from silicon industry. And then we have our specific characterization methods, that how we characterize how the device is looking like and how it's performing in electrical measurements.
This is the second lab where they put the devices they fabricated into a fridge and perform science experiments on them to make sure they work the way that they want them to work. And if they're not, figure out what they need to change to improve them. Why has it been so much harder to make a topological qubit than other superconducting qubits?
It's really, in order to have the topological state, you really need to have the right material combination, and getting to that one is much more difficult.
This is what Larry means by material combination. Their devices are made from layers of different kinds of materials grown on top of each other, and then fashioned into a certain pattern that makes their device, basically a miniature electrical circuit. The specific materials they use and how pure they are all important to the quantum state that they're trying to capture. Larry showed me this image of an interface between two of their materials. These dots are atoms, and the different shades are two different kinds of atoms. And the fact that there's not a single atom out of place is a big deal, as it's really difficult to get atoms to sit together in this neat of a lattice. Normally there'd be holes or cracks, things that we physicists call disorder.
I would say that we call it disorder, has been the major challenge to overcome in order to solve topological gap to begin with. And that has really required a lot of process innovation to maintain this perfect crystalline structure in our materials and have all the interfaces pure enough that we can actually demonstrate the topological phase. Mm-hmm.
Okay, so how does all of this material fabrication build up into a quantum computer? Well, to build a quantum computer, you need to make a tiny controllable quantum system called a quantum bit or qubit. Our normal or classical computers that we use every day, they run on bits that are basically like little binary switches, 0 or 1. Quantum computers, on the other hand, run on qubits, which can also either be in 0 or 1, but also intermediate states, which is the core of what allows quantum computers to solve problems that you can't solve on classical computers. I don't have time to get into why that's true, but I've covered this in the Map of Quantum Computing video, so you can find out more there. But the main point I want to make is that when you want to build your quantum computer, you have to choose which quantum system you want to make it from. So you need to choose some system in physics where you can have a 0 state, a 1 state, and these intermediate states. And so some people choose the energy states of atoms, or the path of a photon or light, or the spin of an electron or atom. These are the many different approaches to quantum computing I was talking about before. But what Microsoft are doing is a bit more exotic. Instead of building their qubit from a single atom or electron, they're building it from a topological property of a whole load of electrons working together. This topological state is called a Majorana zero mode, or Majorana particle. And what this thing is a bit complicated, but this Majorana particle is why this whole topological quantum computing is so interesting. So in an attempt to explain the Majorana particle and what's going on inside a topological qubit, we started playing with Lego, and it ended up being surprisingly useful. Okay, so I've learned a huge amount, and it's all quite complicated, so I thought I'd try and distill it down into the basic elements. And when in Denmark, this seemed appropriate. So the first thing we need to do is get rid of all the disorder and start off with a very clean place. And the first thing we're going to make is our nanowire. That's our nanowire. And our nanowire is made up of many different layers of material that have all been delicately fabricated. And that's what they've been doing in the fabrication lab that I saw earlier. Now, we're also going to have these, which are called quantum dots. And what these are little gates. And these allow, when they're open, they allow electrons to travel through the wire. Or, when they're closed, they trap electrons on. They trap electrons in the wire. And what we can do is we can use this to build a basic qubit, where the state of the qubit is the number of electrons being kept inside the nanowire. And these gates also separate this nanowire from the rest of the circuitry on our chip. Now, if there's an even number of electrons in the nanowire, that can be the 0 state, say, but if there's an odd number of electrons, that could be our 1 state, and the whole system is following the laws of quantum mechanics. And that's what you need to make a qubit, is some quantum system that has got two different distinguishable states. But we need another element, which is to be able to read out the state of this qubit. So we've got another device here, which is the readout, which reads out whether there's an even or odd number of electrons in the nanowire. The trouble with this design is that it's very vulnerable to noise, which is signals, say, from our mobile phone, which could come along and knock off an electron, even cosmic rays, even some temperature. Oh, there. Any of this can disrupt our device and disrupt our ability to control the electrons and also read out their states. Okay, so what's cool about the design of a topological qubit is it makes use of these special particles called Majorana particles. Now, these are going to be our Majorana particles. They're everywhere, but they always come in pairs. But if you can design a chip which splits these pairs apart, what it does is it creates an energy gap which separates and protects the electrons from the surrounding noise. So if some noise comes along, it can even disrupt one of the Majorana particles, but as long as it doesn't disrupt both, the electrons are protected. And these Majorana particles don't stay disrupted for long. If you have a less well-separated Majorana particles, if they're closer together, then the energy gap is lower, and it's also easier for some bit of noise to disrupt both of the Majorana particles at the same time, and that ruins your quantum state. So the whole effort of fabricating these devices about the specific material properties of all of these layers and the specific configuration of everything that they're doing in the fabrication laboratory is to make a device where these Majorana particles are very well separated and there's a large energy gap. And that's the potential of topological qubits, is to make qubits that are much more resistant against noise and disruption than other designs of qubits. Okay, so that's the theoretical Lego version, but Chetan then ran me through the results that Microsoft have actually got so far.
We looked at one of the two pairs of Majorana zero modes. We measured the combined even or oddness, which was parity of that pair. And what we demonstrated is, it's really exciting, is A, we can do it. And we designed the device in such a way that the signal is large. So we managed to keep the noise in the measurement low. Mm-hmm. The signal is large and it's very unambiguous, and we turn it on and it works. So it's really an exciting moment that something that's really a non-trivial piece of information here is shared non-locally across the two ends of a wire, which are 3 microns apart, and we can read it out.
So let me just explain what he means by that. So a qubit needs to have a 0 and a 1 state. And in these topological qubits, this is encoded into whether there's an even or odd number of electrons on the island. But the information about this even or oddness is spread by the Majorana particle to both ends of the nanowire. That's what makes it non-local. And the fact that this 0 or 1 state of the qubit is spread out like this is precisely what makes it resilient, because noise will tend to only hit one place at a time, not both ends at the same time. Now, it's worth saying here that although this readout result is a huge step on the way to operating a topological qubit, to fully harness it, they need to demonstrate another readout on a different section of the device, which is what they're working on now. And then when they have their first fully functional qubit, they'll want to scale up to multiple qubits that can all work together, and then presumably try and catch up with the other companies who currently have hundreds of qubits per chip. But as I've always said, quality is just as important, if not more important, than quantity when it comes to qubits. Okay, but what exactly is a Majorana particle? Well, to explain that, we need to take a little detour into the world of particle physics. So, if you're looking at the rules of physics in our universe, at the very bottom of that, we've got particle physics. Everything is made out of a load of subatomic particles. Protons, neutrons, electrons, quarks, gluons, the Higgs boson. So in the world of particle physics, we've got all of the particles we've discovered. These are the particles in a thing called the Standard Model of Particle Physics, stuff they discovered in particle accelerators like the Large Hadron Collider at CERN. Again, for more context, I've got a map of particle physics if you want to learn more about that. But the important thing to know is in particle physics, as well as all of these real particles that we've discovered, we also have a bunch of particles that people have theorized about, but no one's ever observed in any experiment that we've made. Now, one of these theoretical particles is the Majorana particle, and it's got specific properties like it's its own antiparticle. But if we've never observed a Majorana particle, then what have Microsoft made? Well, the weird thing is that if you get the right groups of atoms together in the right configuration, the electrons of those atoms behave in such a way that it looks like there's another kind of particle there. It's not a real particle, like the ones in particle physics in their particle colliders. It's a quasiparticle, which amazingly has the same properties as a real particle, but those properties come from the collective behaviors of the electrons. A concrete example of a different kind of quasiparticle is an electron hole. This is a gap in between electrons that, when it gets filled in, looks like it moves about kind of like an anti-electron. But there's nothing actually there, it's just the hole in between electrons moving about. The Majorana quasiparticle is a more complicated version of that, but the idea is essentially the same. The collective behaviours of the electrons behave like a particle. So the key takeaway is that particles are things, whereas quasiparticles are emergent properties from other things. And the Majorana particles that Microsoft have made are quasiparticles with topological properties. And it's these topological properties that make them more resistant to noise. So just to recap, if you get the right combinations of atoms together, their electrons start behaving like there's a Majorana particle there. And this Majorana particle exhibits topological properties, which makes it more resilient to noise. So if you build a qubit from this, you can use these noise-resistant properties to build a noise-resistant qubit to use as the basis of your quantum computer. And that just about rounds up this map of topological quantum computing. It's been a fun challenge to try and explain it all. I hope the video was enlightening to you. And it was really fun to go visit Microsoft and see what they're working on. Especially it's in the realm of superconducting nanowires, which was my area of research when I was doing my PhD. And also really cool just to see the beginnings of this brand new form of quantum computing, which I'm very excited to see how it develops in the future. Also, thanks to Microsoft for sponsoring this video, and full disclosure, I had control and final edit over everything you've seen so far, but now we're into the sponsored segment, and this is really cool because basically Microsoft have developed a free educational tool in this realm. It's a website called Azure Quantum, and it's free to use. All you need is a login, and through it you can learn all about quantum computing, programming for a quantum computer, as well as chemistry, because chemistry problems and molecular interactions are a big target area for quantum computers. So I've been playing around with these, and what's cool is it also includes Copilot, which is Microsoft's AI tool, so you can ask it questions, it will answer them, and then also suggest other follow-up questions if you want to learn more. So I've been learning about ATP and also about redox reactions, and then also about superposition in quantum computers and how it's used in quantum algorithms like Grover's algorithm. You can also run things on their software emulators as well, so you can actually write and run your own quantum computer programs, which is cool. So yeah, if you want to learn a load of cool stuff for free, this is a great place to go. It's called Azure Quantum with Copilot, and I've put links to that in the description below. Well, that's it. Thanks again for watching, and a very special thanks to my Patreon supporters. You're all helping me to carry on creating my own free educational content, so I really appreciate your support. Alright, well thanks for watching, and I'll see you again soon on another map video.